Buonasera. Good afternoon. I'd like to present some calculations on null geodesics in perturbed Bianchi type 1 spacetime. My name is... Oh, yeah. Okay. First of all, I would like to begin some reviews on Bianchi type 1 cosmology. The material of Bianchi type 1 material is in conformal metric. We can write like this. The eta is the conformal time, and the gamma ij is the conformal material of spatial part. Then, using the Einstein field equations, we can obtain the equations governing the evolution of the Bianchi type 1 cosmology. Is A is the average scale factor. Is from the first equation is the expansion rate of the cosmological scale factor, and the second one is a kind of acceleration, and the third one is representing the anisotropic structure of the Bianchi type 1 cosmology. Is a shear represented by shear sigma ij is the equation like this, and the last one is the well-known continuity equation. The solution of this is well known, and the scale factor is like this. The first T over T0 term is the well-known flat Friedman part, and Q over T is depends on the anisotropic expansion of the Bianchi type 1 cosmology, and the gamma ij is represented by a parameter SI. SI is depending on the principal axis of the Bianchi type 1 space-time, and the sigma ij, a shear, is time derivative of the gamma ij is represented by like this, and also here SI is determined this shear structure of the shear tensor, and SI is confined by two properties. One is SI, the sum of SI is equal to 0, and SI squared, sum of SI squared is 6. These parameters determine the substructure of the Bianchi type 1 cosmology. Yes, sir. Here we consider the fluid with the radiation and the metal, but after this I only consider the first case. The null geodesic in the unperturbed Bianchi type 1 space-time is defined like this. Here we have the tangent. If we define XA as a null geodesic in the Bianchi type 1 cosmology, then Ka is the null tangent vector of this null geodesic, and here lambda is a kind of affine parameter along the null geodesic, and this null tangent vector must satisfy the dispersion relation and the null geodesic equation. The solution of null geodesic equation is simply you can write like this. The time component is the scalar product of the two null tangent vectors, and the null tangent vector is satisfied like this. And here gamma 0 subscript j is a constant in time. Then another important property of the Bianchi-Taiwan cosmology is the expansion rate. Here we define area of A dot plus sigma j n0I n0j. So A of A dot is a well-known expansion rate, and sigma j n0 n0j is represented the anisotropic structure of the Bianchi-Taiwan cosmology. If here we define normalize the n0I like this, then sigma ij n0I n0j, we can, it was using some calculations, we can represent like this. Here you can see S1, S2 is the component of the shear along the principal axis, and the gamma ij is representing the isotropic structure from the spatial part of the matrix. Then if sigma ij, the anisotropy of the universe is here, it's assumed to be very small, we can approximate this above formula like this. Here Y2 is a kind of quadruple in the sky. That this is important. This creates an important effect on the, if it is true, on the microwave background of the universe. It's a quadruple structure. But this is really well-known, the studies of the Hawking, particularly like this, also Fukaku and Lupin study in item 86 or like that. The photon energy shift I just told about a minute ago. It's here the Z is a kind of redshift, represents the photon energy shift, and it's easily converted to the change of the temperature of the universe. Then here you can see the quadruple nature of the cosmological temperature directly comes is the effect from the anisotropy of the universe. Now turn to the perturbed Bianchi-Taiwan cosmology. Here I process the same procedure like as unperturbed Bianchi-Taiwan cosmology. Here I enter the generalized metric, perturbed metric of the Bianchi-Taiwan space-time like this. Here is A is a perturbed time component of the perturbation, and the BI, CI is the special part of the perturbation. Here, in this calculation, it's important to specify two kinds. One is the decomposition of the perturbed metric. Decomposition means the scalar type perturbations, vector type perturbations, and the tensor type perturbations. And we must impose a JD conditions on this perturbation because the choose of background space-time is arbitrary. We can choose any kind of background space-time. Then with choosing the gauge transformations, we can calculate and numerical calculations we can do. The gauge conditions in this kind we can introduce two kinds of or here is three kinds of gauge conditions. One is a gauge condition for special gauge variables, and the other two is gauge conditions for temporal gauge variables. The special gauge condition is here we call C gauge condition. It's the decomposition of Cij. If we like, if we define like this, then here C bar and Cvi. Here C bar and Cvi is let equal to 0. It's a kind of C gauging. Then another one is we can put B is equal to 0. It's a well-known longitudinal gauge condition. Or otherwise, in other words, it's a Newtonian gauge condition. Or in the if the matter, or here I assume the dust is co-moving with the space-time, in this case we can introduce another gauge condition. The velocity of the dust equals 0 is we call here co-moving gauge condition. With these three gauge conditions, all the perturbed variables become gauge invariants. Then you can easily calculate independent with the gauge gauge conditions. Then now turn to the equations governing the evolution of the perturbations. Here I introduce here three kind of perturbations. One is scalar type, two is vector type, and third is tensor type perturbations. The fluid in the Bianco type 1, perturbed Bianco type 1 space-time, I assume the dust means pressureless. Then I can also assume the sound velocity is equal to 0. And I introduce three special gauge conditions and two for temporal gauge conditions. And the wave number of the perturbations is only propagated along the S3 principal axis of the Bianco type 1 space-time. Then with some calculation or very tedious calculations, we can obtain the difference, a set of difference equations for the perturbed variables. The three is for the scalar perturbations. This phi c is defined by c over 2. It's a kind of potential, and pi a is is a kind of potential in the time component of the matrix. Then delta is the density contrast, I here assume. Then if you can see with the temporal gauge variable conditions, here this is the letter circles all go to 0. Then you can see one can see this is a kind of Poisson equation in Newtonian case. It's the original terms here from the because of the analysis of the universe. Also here is the effect of the analysis of the universe, and all other one is zero, and yes, delta is without this it's a traditional Poisson equation. Plus
this G plus comes from the tensor-type perturbation. If we put tensor-type perturbation is a kind of a 3 by 3 matrix, then we choose it's a kind of a gravitational wave. Here is two polarizations. One is another polarization is 45 degrees from this axis. So I put the G plus is the principal axis. G times I represent the 45 degree polarizations. In this equation, with the perturbative method, then here you see is a traditional Poisson equation appears additional terms, delta or these terms. This is in the usual gauge theory of the Newtonian case, pi a plus pi c equals to 0. 이게 작동 안 하네. Don't work, this doesn't work? Here also you can see the other terms due to the analysis of the universe is sigma bar 33. This all is equal to 0 is another one. Without this 3 bar 33, sigma bar 33, we can obtain the usual Newtonian potential condition, pi a plus pi c equals to 0. Also, the density contrast, the difference gauge for the density contrast, we can have this is a traditional Friedman case. It's there's a kind of a driving force, a system, or due to the gravitational wave, you see. And this is the vector equation for the vector. This is the giza for the gravitational waves. Also, some additional terms you can see here due to the analysis of the universe. This G plus term coupled with the density perturbation is solely due to the analysis of the universe. If the anisotropy of the universe disappears, then all the sigma terms disappears. We can recover the of the flat Friedman space-time. This solution of this equation is studied, and you can find in the literature. Now, return to the main topic of this talk is null geodesy in perturbed type 1 model. Here, I approach this subject with the perturbative method. I write the null geodesy is a background term plus a perturbed term. And the corresponding tangent vector also background plus perturbed term. Also the crossover symbol, we can write this background plus perturbative term. Then the dispersion, from the dispersion relation, we can, for the background and for the perturbative, perturbed terms, and the null geodesic equation becomes for the background and for the perturbed space-time. Here, AAD is a kind of matrix or tensor. It's defined by this. This AAD should be recovered from the background terms. And FA is a kind of a driving term or source term. It's the perturbative part of the crossover symbols. Then, using the matrix of the perturbed Young-Taiwan spacetime, we calculate these terms and putting this results into this perturbed null geodesic equation, we can obtain a set of differential equations here. H0 is defined by, here is not. It's sigma ij, n0i, n0j. And sigma ij is a shear, and this is a time component. This is for the special component of the perturbation. We can write this form. Here also sigma ij, h0 is are coming from the anisotropy of the Young-Taiwan space-time. Then here you can see if h0 sigma ij goes to 0, then we can obtain the usual null geodesic equation for the flat space-time. And F0 is the time component of the driving force. Fi is the time component of the driving force. Here, I decompose this two terms. The first part is the scalar type perturbations. This is due to vector type perturbation, and the sigma Tij is due to tensor type perturbations. Also, Fi, the special part component, is decomposed into the three parts. Into the three parts, you see. And the solution of this can easily obtained using a kind of matrix differential equation. If we put a set of differential equation, delta and NA is defined by this, and from the above equation, we can put these forms. Then this delta NA with this equation set a kind of differential equation, namely a matrix differential equation, a form like this. X is two component. This is four components. Delta N also has four components. Then M is a 8x8 matrix, and F is like this. Then the solutions, well known. You can find any textbook for the ordinary differential equation or dynamical differential equations for the dynamical systems. You can obtain the component of this PAB is a matrix like this. Then, if you have time, you can check all these components of the null geodesic. It's a scalar part. Scalar part. It's the time component and the spatial component. Vector part is a time component and the spatial component. Tensor part is a time component and spatial component. Also, you can check the null tangent vector is scalar part. Scalar type is time and spatial component, vector or tensor. Now, I'd like to give one application of this perturbed null geodesic perturbed part of the null tangent vector. If the time component of the null tangent vector, we can easily calculate the photon energy shift in the perturbed magnetized space-time. As before, in the unperturbed magnetized space-time, we can put the null tangent vector and the time-like force velocity. It's like you can put like this. Then you can obtain this scalar product. You can put like this, and the photon energy according to the photon energy shift formula, we can obtain the red shift of a photon, which is propagating through the perturbed magnetized space-time. We can express like this. This is the it is due to the perturbed magnetized space-time, and this term is directly obtained from the delta n0 of the perturbed magnetized space-time. We can put all this. Also, I can show this explicitly. The scalar part is the scalar part of the photon energy shift is this is the usual freedom part plus the terms due to the anisotropy of the magnetized space-time. Is here you can write this form, and also the vector form is like this, and the tensor form is like this. Also, from these equations, if we put, if you assume the anisotropy is all is equal to 0, then we only have yes, it's also my problem.
같은데. 예. This is a solvable by results. Say, if the anisotropy of the space-time disappear, then the P is a kind of a delta Ij, becomes delta Ij. Then P0I, Pi0I, all these terms disappears. Then we can recover the for the flat Friedmann space-time. Also, the vector type perturbation, we can the same result, and the tensor type perturbation, we can obtain the same results. I did many calculations about these terms, but at this time I stop here. Thank you very much. Stability? Here's no problems about, I think, stability. Because the photon propagate along the, through the perturbed Young type 1 space-time, then the perturbed part of the, in other words, the perturbation effect, or the trajectory of the photons, then we can observe in the observation, at the observation point only the result of the perturbations. That's all. Yes, in this case, yes, yes. In the I have shown that in the unperturbed case, the expansion rate of the Bianca type 1 space-time, the second term is depends on the anisotropy of the Bianca type space-time. This term affects strongly the propagation of the photons. Is depends on the direction. If in this calculation, if the photons propagate along the principal axis, there is no anisotropy you can observe. Because you can see sigma theta pi, theta, or you said theta equal to 12 pi, it's like that, then the quadrupole term disappears. Yeah.
Okay. My topic is exact solution of the cosmological fluid equations for Newtonian stars. Well, all of you are talking about general relativity, black holes, and so on. Here, I'm going to talk about Newtonian gravity. When I heard of the ICRA network workshop, I was wondering if my topic is proper for this workshop. So I asked about it Professor Hyung-won Lee. She told me that I can talk about anything as long as it is related to gravity. So here I am. Well, expansion and contraction, including collapse behavior of a star, have always been an interesting subject not only in general relativity but also in Newtonian gravity as well. A proper treatment for the subject would be so complicated that most work on the subject has employed numerical code. But to my opinion, it is very important to get an analytic result, to get some feeling for what can happen during the process. So here I would like to present a simple analytic result for stellar equilibrium and collapse. So let me begin with the equation of continuity. This is equation of continuity. This is the Euler's equation. This is Newton's equation. And U is the fluid velocity. In other words, here U is the fluid velocity. In other words, the velocity of the mass point of a star. And phi is the gravitational potential, G is the gravitational constant. Most work on the expansion and the contraction of a star has presumed the adiabatic process which leads to an equation of state called the polytrope. This is the equation for the polytrope. Here, instead of the polytrope, I would like to consider the ideal gas law for the equation of state. This is the ideal gas law. The reason why I consider the ideal gas law instead of the traditional polytrope is because, first, it characterizes the kind of system which also deserves some attention in its own right. Second, because of its simplicity, I may be able to get some analytic results which might lead to further insight on stellar behavior. Without the viscous dissipation, the first law of thermodynamics, in other words, the law of energy conservation, is given by equation 6 here. Also, the ideal gas law here, together with the enthalpy equation in thermodynamics, lead to equation 7. So actually I have 5 equations. Equation of continuity, Euler's equation, and Newton's gravity equation, ideal gas law, and first law of thermodynamics. Or instead of the ideal gas law, I can use this equation 7 to solve 5 unknowns. In other words, U, phi, pressure P, density, and T. To solve the equation, I'm suggesting the ansatz the following ansatz for the velocity and the density. Here, large R log t is the radius of a star at time t, and the density is given by this. The constant A and B will be determined later. So I'm going to use these ansatz to solve those 5 equations. From equation 6 and 7, if I eliminate divergence of heat current density, then I have equation 9. At the center, the ansatz and this equation will yield immediate equation 10. And the solution of equation 10 immediate is that at the center, the ideal gas storm holds. In other words, what I'm doing is okay. Also, I want to assume that the polytrope condition holds only at the center. The traditional assumption of polytrope holds everywhere in a star, but I only assume the polytrope only at the center. And this assumption is equivalent to the assumption that the center is neither heat source nor heat sink. But if there are nuclear explosions in the central region, then this condition is no longer valid. But I'm not considering nuclear explosions here. This assumption, in other words, the polytrope holds only at the center, is different from the traditional assumption of polytrope. The traditional assumption of polytrope is an equation of states like the ideal gas law. But the polytrope holds only at the center is kind of a boundary condition for the solution of equations to satisfy. So there's some difference here. With the ansatz and the assumption of polytrope at the center and many trials and errors, I'm able to obtain the pressure, temperature and density and potential in terms of mass m and radius of a star in this compact form, equation 13. As you can see here, the ideal gas law holds. Also, the constant A and B of the ansatz are determined. And the radius R at the time t should obey this differential equation, equation 14. And equation 14 can be solved by the standard energy method if we convert this equation 14 into the form of equation 15. This is exactly the same form as the total as the law of conservation of total mechanical energy, and so V correspond to potential energy and epsilon correspond to the total energy. And the solution of equation 14 here is given by an elementary integral, equation 17 here. Plus and minus correspond to the case of expansion and contractions, respectively. So we can consider the contraction from the initial radius, say R is R maximum, with the zero velocity at time t equals 0. That means at the maximum radius, the energy is equal to the potential energy. And the potential energy curve looks like, for gamma, greater than 4/3 looks like this, and potential energy gamma less than or equal to 4/3 looks like this. So from this curve, it's clear that there is no bound state for gamma greater than 4/3. In other words, it oscillates between maximum radius and minimum radius. For gamma less than or equal to 4/3, there's no stable bound state. In other words, the star will collapse. For star with gamma greater than 4/3, one can find the stable radius. In other words, this point. And it is given by equation 19. Also, we can find the frequency of small oscillation with respect to the stable radius. In other words, if star oscillates here, we can find the frequency of small oscillation. And it is interesting to compare this with the previously obtained frequency, namely Weinberg also obtained the frequency, Zeldovich and Novikov also obtained the frequencies. Equation 21 is the Weinberg frequency, and equation 22 is the frequency obtained by Zeldovich and Novikov. But Weinberg derived his frequency from the very simple model of uniform dilation and contraction of a uniform sphere. Zeldovich and Novikov also used the oversimplified models of average density and average pressure and so on. Their derivation have nothing to do with the general relativistic equations or Newton's cosmological fluid equations. But mine is based on the exact solutions. Let me consider star with gamma equals 4/3 in detail. From the previous solutions, previous equations for radius r of time t, we can immediately find the radius in terms of time t, equation 23. And this agrees with the result of Oppenheimer and Snyder's calculation of gravitational collapse, which used full general relativistic equations, but they used the assumption of zero pressure and temperature everywhere. Actually, if one solves equation of continuity, Euler's equation, and Newton's gravity equation with the assumption of zero pressure and zero temperature, one can have the exactly same solution, same result of Oppenheimer and Snyder. And this actually corresponds to the case of gamma equals 1. Of course, this result is invalid as the radius of a star becomes order of GM. Then the full general relativistic effect should be taken into account. But a star spends almost all of its time to shrink to 1/1000th of its initial radius. You should remember that. Finally, the summary and discussion. Obviously, for stellar expansion, star can expand forever if energy is greater than or equal to 0. Otherwise, a star cannot expand forever, and that's quite obvious. For stellar contraction, a star with energy less than 0 oscillate if gamma is greater than 4/3, and collapse if gamma is less than or equal to 4/3. Well, the mechanism of stellar expansion and contraction can be discussed by the heat flow into a sphere of radius, say, small r in a star during the expansion and contraction. So the heat flow is given by equation 24. So from equation 24, if gamma is greater than 4/3, when a star expands, heat flows radially outward, so that the pressure is getting smaller and smaller in comparison with the gravitational attraction. Therefore, the expansion will slow down. On the other hand, a star contracts, heat flows radially inward, so the pressure gets bigger and bigger to dominate over the gravitational, which prevents a star from collapse.
For gamma less than 4/3, exactly the opposite takes place. In other words, when a star expands, heat flows radially inward, so that the pressure is getting bigger and bigger in comparison with the gravitational attraction, which helps the star to keep expanding. Of course, the star will stop expanding when the heat flow stops. During the contraction, the heat flows radially outward, so that the pressure gets smaller and smaller in comparison with the gravitational attraction, which makes the star collapse. Well, as a byproduct from the solution that I obtained, the central density, temperature, and pressure of a stable star are given by this compact formula. So with this compact formula, the central densities, temperature, pressures of the Sun, Jupiter, and Saturn are calculated and listed in table. This first one is Sun, second one is Jupiter, third one is Saturn, and the upper values are previously estimated values. The low ones are the ones that I calculated from my solutions. Obviously, there are some discrepancies because, first of all, for Sun, I did not consider nuclear explosions. The other reason is because stars have presumably hard cores, which do not obey ideal gas laws. But anyway, those previous established values are model dependent. Well, this is it. Thank you for your listening. Sure, that's why I have first law of thermodynamics, and that's why I'm using enthalpy equation. The spin?
The sound can be greater than the electrical time for thermal equilibrium.
Well, I did not consider. I did not mention the polytrope everywhere. I mean, I do not use the polytrope condition. I use ideal gas law. Polytrope is holds only at the center, not everywhere. Yeah.
You may not maintain thermal equilibrium. So it's more
I mean, Yeah, you are right. When a star oscillates very rapidly or contracts very rapidly, there's no time for heat flows. So people assume the polytrope. You can do that, but this is very. I'm trying to find exact solution for very simple system.